Hello friend, welcome to this lecture, and in this lecture we will discuss a very important second order linear partial differential equation, homogeneous equation, and that is known as wave equation. And if you recall, at the time of classification we have discussed the problem like L of u equal to f of x, y, z, p, q. So, let me write it here. So, you consider the following second order semilinear PDE L of u plus g of x, y, u, ux, uy. Here this u is a function of x and y, and L is the differential operator, in fact linear differential operator defined as L as r divided 2 u divided 2 upon divided 2 divided x square plus s divided 2 divided x divided y plus t divided 2 divided y square, and these coefficient r, s, t are continuous function of x, y. In fact, we call this kind of equation as linear equation if it is linear in highest order derivatives. So, here highest order derivative is second order, and if they are linear in terms of say x, y, we simply write it that x, y that this is a linear differential equation. So, now we have already observed that during classification of second order linear partial differential equation, that by suitable choice of new coordinates which we call as characteristics, any equation of the type 1, this kind of equation can be reduced to one of the standard canonical form, that is elliptic equation. Here your form is uxx plus uyy equal to some function of x, y, u, ux, uy, and parabolic equation means say ux equal to uyy plus g. Similarly, hyperbolic equation means uxx equal to some constant times uyy and so on. So, here this elliptic equation we call this is as elliptic equation if s square minus 4 rt is less than 0, where s is the coefficient of mixed partial derivative, that is derivative 2 upon derivative x derivative y, and r is the say coefficient of derivative 2 upon derivative x square, and t is coefficient of the other double derivative that is derivative 2 upon derivative y square. So, if s square minus 4 rt is less than 0, then we call this equation as elliptic equation, parabolic equation when s square minus 4 rt is equal to 0, and hyperbolic equation is when we call s square minus 4 rt greater than 0. And we say that when we have this equation, then with the help of characteristics we can convert equation of these type into a prototypical problem, and in this lecture we will discuss one prototype that is corresponding to hyperbolic equation. And we say that if our problem is hyperbolic equation, then we can always reduce our problem into this form, that uxx equal to uyy some constant times uyy plus some function g x, y, u, ux and uy. Now, in this lecture we simply consider the homogeneous part, that is uxx equal to k uyy, where is k is some constant. So, here we are considering the one dimensional wave equation given as follows, that is utt minus c square uxx. Here t we consider as a time and x is considered as a space variable. So, here we call it one dimension because it is one dimension in space. So, we call one dimension wave equation mean utt minus c square uxx equal to 0 because we have only one dimension space variable is involved. So, now this equation 2 represent a prototype equation of hyperbolic type second order linear partial differential equation in two independent variable, and you can check easily that here the s is equal to 0, r you can consider as minus c square and t equal to 1, and you can calculate the value of s square minus 480 which is coming out to be positive. So, it means that this wave equation is a hyperbolic equation, and you can see that any equation of hyperbolic type can be converted into this kind of simpler form. Now, here we have already discussed, in fact it is done in this lecture, that in this case we can choose our characteristic lines. It means that new coordinate axes like xi equal to x minus ct and eta equal to x plus ct here. So, when we use these characteristics, then we can write down our derivative uxx utt in terms of nu xi and eta, and you can write uxx u xi x plus u eta x, then you can write it u xi plus u eta, and ut equal to u xi t plus u eta t. Here we are simply using the chain rule that u is a function of xy and xy is a function of xi eta. So here we are finding the other way around, that u is a function of xi eta and xi is a function of x and y. So I want to find out derivative of u with respect to x, then u xi x, u xi y. So that is what we have written here. So ux is u xi x plus u eta x, because u is a function of xi and eta, and xi and eta are function of x and y. So we are writing like this. Here y is your t. So we can write ux as u xi plus u eta and ut as c times u eta minus u xi. So if we write down in operator form, then we can write dev by dev x as dev by dev xi plus dev by dev eta, and dev by dev t you can write it c times dev by dev eta minus dev by dev xi. So you can write dev 2u by dev x square is kind of square of this operator, that is dev by dev eta plus dev by dev xi whole square operating on u. So when you simplify, you will get this term that u xi plus 2 u xi eta plus u eta eta, and similarly you can calculate dev 2u by dev t square, and that is coming out to be c square into u xi minus 2 u xi eta plus u eta. When you put it into this equation, that uxx equal to c square utt, I think it is the other way around, it is 1 by it is c square utt equal to, let me write it here, it is utt equal to c square uxx. So when you use this, you can see that your equation is now reduced to 4 u xi eta equal to 0, because here utt is what? Here utt is c square u xi minus 2 u xi eta plus u eta equal to c square times u xi plus 2 u xi eta plus u eta. Now these will be cancelled out. What you will have is this, that 4 times c square u xi eta is equal to 0. Now c square is just a constant, and which we have taken as non-zero, so c can be taken out. In fact 4 also you can taken out, and you have u xi eta equal to 0. So this is the this is why we always try to find out a new coordinate axis where our equation can be modified in a simpler format. Now here this wave equation utt equal to c square uxx is now reduced to u xi eta equal to 0, which is quite easy to solve. And if you can solve this, if you integrate with respect to xi and then eta, you will get the following formula, that u xi eta equal to phi xi plus xi eta. In fact, when you integrate with respect to eta, then u xi is equal to is a constant basically, because it is 0. So if you look at the constant, then the constant will be constant with respect to xi here. So you will get a xi here, and then when you integrate this, you will get what? It is integration of a xi plus some constant with respect to eta. So you will get some kind of formula there. So we can write this as some function of xi and some function of eta. Here phi and psi are some arbitrary function. Now by replacing xi and eta, because these are intermediate variables, so we can write xi and eta in terms of x and t. In fact, we already know xi as x minus ct and eta as x plus ct. So we can write our solution uxt as phi of x minus ct plus psi of x plus ct of this equation, that is utt equal to c square uxx. So this wave equation has the following form. Here phi and psi are some arbitrary function, and we can use initial arm boundary condition along with this equation to find out these arbitrary variable, that is phi and psi. Now so this is this we have obtained using only the characteristics equations. So here now how we can utilize this to find out a solution of wave equation defined in an infinite ring. So consider the following one dimension wave equation, dev 2u by dev x square equal to 1 upon c square divided to u by divided t square. Here x is lying between minus infinity to infinity, and t is a time which is greater than 0, and at time t equal to 0 we have certain condition. So we already seen that the general solution of the PD is given as u equal to f of x plus ct plus g of x minus ct, where f and g are arbitrary constant. Here I have just taken f and g, in previous slide we have taken phi and psi, so no problem, because these are arbitrary constant which we have to say remove to in order to that it satisfies certain given condition. So here we will discuss that how this solution can be used to describe the motion of an infinite string. So let us move here and suppose that the string is of infinite length. So here we have string, and at time t equal to 0 the displacement and the velocity of the string are both given as a function. So it means that at t equal to 0 it is not in a equilibrium position, in fact it is in disturbed position. You have infinite string, you take some point and disturb this. So it means that it may not looking like this, it may be of something like this, maybe this or any form. So here we say that this is your x axis, and you simply say that at this point your displacement is this, and it may not be in a static position, it may have some velocity. To we say that the at point x your displacement is given by f of x, and at this point it may have some velocity of displacement, it may move like this. So it means that we have some velocity also, so we call it w by w t equal to g of x at t equal to 0. So at the initial point t equal to 0 it may have displacement from the equilibrium position, that is this x axis, and it may have some velocity, we call this as g of x at t equal to. So this is the initial condition which we are talking about. Now we want to find out a solution satisfying these initial conditions. So it means that you find out your small f and small g in terms of capital F and capital G. So we already know that u equal to fx means u is a solution of u is a function of x and t. So it means that what is given here, that is u of x0 is capital F of x, and w by w means w by w at x comma 0 is your g of x. So using this you put t equal to 0 in previous here, if you put t equal to 0 then ux0 will be what, ux0 is simply f of x plus g of x, and you can write it here that f of x plus gx is equal to ux0, that is f of x. Similarly if you differentiate with respect to t, what you will get, ut x 0 is equal to, when you differentiate you will get f c f with respect to x plus ct. If you differentiate this, what you will get, in fact let me do it. So here when you differentiate this, you differentiate f x plus ct with respect to x plus ct, and then you differentiate x plus ct with respect to t, that is your c will come into picture. Similarly your g, so you will get z dash x minus ct, and then you differentiate x minus ct with respect to minus c, that you minus t, that will give you minus c. So derivative, this derivative f dash means d by d of x plus ct of f x plus ct, because f is a function of only x plus ct. So f dash means derivative of f of x plus ct with respect to x plus ct, and then you use chain rule and you differentiate x plus ct with respect to t. So you will get your utx0 as this. So and put t equal to 0. So when you put t equal to 0, you will get c f dash x minus c g dash x. So we have two relation and two unknown to remove. So you with the help of this you need to find out small f and small g, and since in second equation we have derivative, so we differentiate the first relation, and you can say that f dash x equal to small f dash x plus g dash x, and then use you write down c here and then you add. So in this way you can get f of x minus g x equal to 1 upon c. When we differentiate, okay, let me do it here. So here we have this, and your gx is equal to c f dash x minus c g dash x. When you sum this up, you will cancel out. So, we will get 2c f dash x equal to c f dash x plus g of x, but we want to find out f x. So, we simply integrate it. When you integrate, you will get 1 upon 2 f dash f of x plus integration g. Now, integration you are doing with respect to x. So, let us take that it is starting from some arbitrary value, let us say a to some x here and g xi d xi. So, that is what we are writing here, that I can write f x minus g x equal to 1 upon c b to x g xi d xi. Here b is just a arbitrary constant. Now, similarly you can simplify and you can get f of x as 1 by 2 f of x plus 1 upon 2 c b to x g xi d xi, and g x as 1 upon 2 f of x minus 1 upon 2 c b to x g xi d xi. So, once we have arbitrary value the value of arbitrary constant, by assuming that your equation will satisfy initial condition, that is u equal to f of u equal to ux 0 is equal to f of x at t equal to 0 and ut x 0 is equal to g of x. And once we have f of x and g of x, then we can write down our relation solution uxt as follows, that uxt is equal to 1 upon 2 f of x plus ct plus f of x minus ct plus 1 upon 2 c x minus ct to x plus ct z xi d xi here. So, it means that at a point you can find out, so here u represent u of xt. So, it means that solution u of xt is written as 1 upon 2 f of x plus ct plus f of x minus ct plus 1 upon 2 c x minus ct to x plus ct z xi d xi here, and here f and g is already known because it is given in terms of initial condition. And this solution 12 is known as D'Alembert's solution of the one dimension wave equation, in fact wave equation in infinite string. Now, if you look at here, I can draw this here we have this x, here we have t x's, and here we have the point x of x and t at which we want to find out the solution. And at this point, if you draw your characteristics, so characteristics are what, x minus ct and x plus ct here. So, x minus ct you can write it a line passing through this and here. So, if it is, so it means here we have x minus ct, let me write it point x naught t naught. So, x minus ct equal to x naught minus ct naught. So, here this is the point x naught minus ct naught comma 0, and here this line is x plus ct equal to x naught plus ct naught, and this point is given as x naught plus ct naught comma 0. So, it means that we look at the point say x naught t naught and we want to find out our solution at this particular point. Then we can draw two characteristics passing through this point x naught t naught, and one characteristic is this, that is x minus ct equal to x naught minus ct naught, and another characteristic is x plus ct equal to x naught plus ct naught, and we say that it forms a kind of triangle whose name is PAB, where P is the point at which we want to find out the solution and A and B are points on x axis. So, if you look at your equation number 12, I can look at the solution as u at P equal to 1 upon 2, and here f x plus ct is a point here. So, f of B plus f of x minus ct is this point, f of A. We are looking at the solution at x naught t naught. So, everywhere it is x naught x is replaced by x naught and t is replaced by t naught. So, I can write it 1 upon 2 f b plus f of a plus 1 upon 2 c. Now, x minus ct is basically your a to b z xi d xi. So, it means that if you want to find out a solution at p, I must know the value of f at point A and B. So, it means that f value I should know at these value, and the value of g between A to B, means in this entire region I need to know the value of g. So, we say that any point form give you a region, right, and we say that it is the line AB on which your solution at point P depend, and we call this domain as domain of dependence. So, it means that if you take any point P, then the solution will depend on the data of f and g given on this line AB and the endpoint of AB. So, and one more important point, that if you take any point in this triangle, say here, then here if you find out the solution, again your solution will depend something like this. So, it means that if you take any point inside your triangle, your domain of dependence is a subset of this AB. So, this this domain we call is domain of dependence. So, it means that solution of P is depending on the line AB, and which you can obtain by drawing two characteristic lines passing through this P, and it will form a triangular region, and the base line is called domain of dependence. And similarly, I can find out, say, region of influence. If you look at the same feature again, so here we have this point P, and we say that this will determine some kind of domain of dependence. Now, if you look at any point this, then I can have a, say, characteristic line like this and characteristic line this, right. Here this characteristic line, if you take this point as, say, x1 comma 0, then this characteristic line is what, x plus ct equal to x1, and this is what, x minus ct equal to x1. So, we say that if you make a triangular region. Now, what this region is, we call this region as region of influence of x1 comma 0. Why? Because if you take any point in this region, right, and draw your, say, characteristic, then this point will come into picture. So, it means that the solution in this region, if you take any point in this region, the solution at that particular point is influenced by the point x1 comma 0. So, we call this region, upper region, this region as region of influence of this point x1 comma 0, because if you take any point in this region, say here, and if you draw your domain of dependence, that must contain the point x1 comma 0. So, we say that a point on x axis will define a region in which every point, if you take any point in this region, their solution must depend on x1 comma 0. So, we call that this region is your region of influence of x1 comma 0. And similarly, if you take any point here P, then it will give a triangular region, and you say that the base will give you a domain of dependence, that solution at P will depend on this baseline. So, we call this as domain of dependence, and this region as region of influence. So, it means that that is the basic thing which we want to connect with these D'Alembert's solution of one dimension wave equation. Now, we will move forward, and we say that if the string is released from rest, it means that the initial at time t equal to 0, if that string will not have any kind of velocity, it is just a static kind of thing, that your it is static and it may be displaced, right. Then in this case your solution is given by u equal to 1 by 2 f of x plus ct plus f of x minus ct, and if you look carefully, then it is what? It is basically, it is this displacement at given point x and t is now produced by two pulses of shape, that is u equal to f of x plus ct and f of x minus ct. So, basically these are two disturbance, and when you join together, look at the resultant, then that will give you the shape at the point x comma t. Let us say that one f of x plus ct is moving in one side, another f of x minus ct is moving the other side, and we say that these are two disturbance moving in opposite direction, and the resultant will give you the linear combination of 1 by 2 of f of x plus ct plus f of x minus ct. So, we say that basically the subsequent displacement of the string is produced by two pulses of shape u equal to 1 by 2 f of x plus ct and 1 by 2 f of x minus ct, each moving with velocity c, one of the one to the right and other to the left, right. And to understand this phenomena, let us consider that what actually it is happening in equation number 13. So, let us say that your initial shape is given by this. So, your initial shape, let us assume that here we have the point minus a and here we have a, and we say that your initial displacement is 0 and rest it is 0. So, it means that your string is looking like this. Here we have it is infinite string, all other places between minus infinity to minus a and a to infinity it is lying on the rest, but between minus a to a it is basically the 1 position. And so, that is what we say that f of x is given as 0, x is less than minus a, 1 when mod of x is less than a, and 0 when mod of x is bigger than a. In fact, x is bigger than a. So, here this is your initial displacement given, and we assuming that g is equal to 0, it means that it will not have any velocity. Now, to look at here, let us look at some times like t equal to a by 2c. So, at time t equal to a by 2c, because this now it is free to say oscillate, free to move. So, when we make it free to move, then we try to find out what should be the shape at different times. So, at t equal to 0 it has this shape. Now, let us say that t equal to a by 2c, what should be the shape. So, here we know that at any point your shape is u x t equal to 1 by 2 f of x plus ct plus f of x minus ct. Now, at t equal to a by 2c I want to write. So, it means that u x a by 2c will be equal to 1 by 2 f of x plus ct is a by 2. So, x plus a by 2 plus f of x minus a by 2. So, I just want to find out the value of f of x plus a2 and f of x minus a2. So, let us find out x plus f of x plus a2. So, using this definition I can write 0 when x plus a by 2 is less than minus a, and 1 when x plus a by 2 lying between minus a and a, and 0 when x plus a by 2 is greater than a. And when you can simplify, you will have this relation that f of x plus a by 2 is 0 when x is lying between minus 3 by 2 a and 1 between minus 3 by 2 a to a by 2, and when 0 is when x is bigger than a by 2. Similarly, you can find out the value of f of x minus a by 2, and you can simplify and you can have this, that 0 when x is lying between minus half a and 1 between minus half a to 3 by 2 a, and 0 when x is bigger than 3 by 2 a. And what we want to write, at t equal to a by 2c, the shape u is given by sum of these two, and if you want to draw, what you will get, that your initial let me write it here, this will give you the initial step. So, that is minus a to a. So, here minus a to a, and here it is minus a, and here we have minus 3a by 2, here minus a, here it is a by 2, here minus a by 2, here a by 2, a and 3a by 2. So, let us look at the shape is right now is this, it is 1 here. Now, here 0 between x, so till here it is 0 and here also it is 0, and between minus 3 by 2 a to minus 1 by 2 a, it is 1 by 2. So, let us say that this disturbance is half, and then between minus a by 2 to a by 2, minus a by 2 to a by 2, it is 1. So, let us say that it is 1, and then again it is this thing. So, now your disturbance is now moved like this, that between minus a by 2 to a by 2 it is 1, and between minus 3a by 2 to minus a by 2 it is just half, and similarly here. So, it is kind of a symmetric shape we are moving. Now, it is the time at t equal to a by 2c. Now, look at here, now look t equal to a by c, then we at t equal to a by c, your u x t will be what? U x t is equal to half of f of x plus c t, x plus c t is a. So, f of x plus a plus f of x minus a. So, I need to find out the value of x plus a and f of x plus a and f of x minus a. So, using the same technique we can find out f of x plus a is this, the 0 when x is less than minus 2 by a, and 1 between minus 2a to 0, and 0 when x is bigger than a. Similarly, f of x minus a also, and when we can write uxt, I can write it here that it is 0 when x is less than minus 2a, and 1 by 2 when minus 2a to a, and 0 when. So, let me again repeat the same thing. So, here it is t equal to 0, t equal to a by 2 c, and t equal to a by c. So, it is minus a to a, rest it is 0, and here it is say here it is this, and minus 3a by 2, so 3a by 2, and minus a by 2, a by 2. So, this we have already seen. Now, here at t equal to a by c, between minus 2a to plus 2a, it is 0 here, here also, and between minus 2a to a, it is half only. So, it is now reduced to half. So, it means that initially shape is this. Now, when your string is vibrating, then your disturbance is trying to move away from the initial position, that is from this point, and it is moving towards this and this. So, we say that it is your magnitude is now divided into two parts, and one is moving here and one is moving here. So, at t equal to a by c, now it is almost moved here. Now, let us consider one more point, that is t equal to 3a by 2c, and we want to see what should be the behavior here. So, to find out, let us say t equal to 3a by 2c, and here we x plus ct is f of x plus 3 by 2a, and we have calculated it like this, f of x minus ct, that is f of x minus 3 by 2a, and we have calculated like this. Then we can write down at t equal to 3a by 2c, the shape of the string becomes u equal to half of f of x plus ct plus f of x minus ct, which is nothing but 1 by 2 f of x plus 3 by 2a plus f of x minus 3 by 2a, and 0 between say 0 when x is less than minus 5 by 2a, and 0 when x is greater than 5 by 2a, and between minus 5 by 2 to minus a by 2, it is half. Let me draw it here. So, minus 5a by 2 somewhere here, minus 5a by 2, minus 2a, and somewhere here it is minus a by 2, somewhere here minus a by 2, and somewhere. So, here it is a by 2, and somewhere here it is 5a by 2. So, it is minus 5a by 2, it is 0, no problem, and then between minus 5 by 2 to minus half a, it is 1 by 2. So, between here to minus a by 2, it is half. Similarly, here a by 2 to 5a by 2, it is half, and sorry here then 0 between minus half to half, and again half a to 5 by 2, it is half, and so on. So, I can draw like this, whatever we have drawn is at t equal to 3a by 2c and t equal to a by c. Now, if you look at carefully what is happening. So, basically it is the initial disturbance, and disturbance is created say symmetric about this. Then as time passes from 0, then this disturbance is now trying to distribute into two equal parts and trying to move away from each other. And if you look at the area is still 2a, right, that you can calculate, and when you look at t equal to a by c, your it is spread in a longer period, but still area is your 2a only. And if you look at t equal to 3a by 2c, now this disturbance is say move apart, and now it is distributed into two equal disturbance, one is moving this side and one is moving this side. Is it okay? So, here you can say that here the initial disturbance is now distributed into equal disturbance, and area will remain the same. It means the disturbance is now distributed exactly into two parts, and one is moving this side and one moving in other side. So, we can say that here it is kind of a wave propagating in two different direction, and this you can see very easily when you have some kind of pond or some kind of gathering of water, and if you put some kind of stone, then you will see that there is some kind of vibration coming to be, some kind of vibration is coming, and they and these vibrations are moving from the point where your stone fall. So, from the point of disturbance it will try to move in all the directions and moving away from that, and it is looking like a wave, that wave is moving from that particular point of disturbance. And since we are considering only say one dimension, so here we have only left hand side and right hand side. So, here it is the disturbance is moving in opposite direction and having the equal kind of behavior. So, we call this kind of behavior as wave. So, we can say that here f of x plus c t is half wave and it is another half wave. So, we say that here because of this we can say that it is sum is sum of two equal disturbance, or say wave, one wave is moving right and one wave is moving left. So, here we have seen that we have taken a particular example to show that that solution is behaving like a wave, how a disturbance is say distributed in two equal part and moving away to each other. So, here I will stop, and so in this lecture what we have discussed, we have discussed the use of characteristic lines to find out the solution of an infinite string, and that solution we call as D'Alembert solution, and it is given by the following thing, that u x t equal to half f of x plus c t plus f of x minus c t plus 1 upon 2 c x minus c t to x plus c t is design, and we have discussed domain of dependence and region of influence, and in continuation we will discuss some more kind of a domain. For example, here we have considered an infinite string. What happen if this string is not infinite, in fact it is a semi infinite or finite or some kind of two dimension region, that also we want to discuss, and that we will discuss in coming lectures. So, here I will stop. Thank you for listening us. Thank you.